Okay, so let me just put up a little example of a string first, A, B, D, A, B, C, A, and we end it as usual with a $sign, and the $sign is smaller, lexicographically smaller than any other character in the alphabet. And then a suffix tree for this, all right, that's the suffix that begins at position 6. Actually, let's 1, 2, 3, 4, 5, 6, 7. So CA, $sign, begins at position 6. And then we have another A, B, D, A, B, C, A, $sign. That's position 1. And this is the suffix for position 7 is just A, $sign. And then A, B, C, A, $sign. That's position 4. A, B, C, A, $sign. Yep, that's right. And then B, C, A, $sign. That's 5. And D, A, B, C, A, $sign. That's 2. And one more. That's D, A, B, C, A, $sign, which is position 3. Okay, so there we have a suffix tree for this string. Hopefully I've done that correctly. And this is the root. Okay, now a suffix array is a more compact, I shouldn't say it's a full representation of a suffix tree. We need some additional information from a suffix array in order to get a suffix tree, and we will discuss that later. But a suffix array is a different representation of the set of all suffixes of the string in a way that is more compact than a suffix tree. It's easier to build and faster. And since the revitalization of research on suffix arrays have mostly supplanted the applications that suffix trees were useful for. I'll say a little bit more about that later. But what is a suffix array? A suffix array is a list of positions from 1, in this case, well, I might as well put 8 in here, although sometimes we neglect a position for the, I think I am going to neglect it. Neglect a position for the end of string character. But it is a list of integers, positions, which tell you in lexicographic order what the lexicographic order of the suffixes are. So let me put this down. I want to be on the same board. So the suffix array is often called pos, or position. And here's the suffix array for S. It's 7, 4, 1, 5, 2, 6, 3. And what does this mean? It means that if you look at all the suffixes of this string, excluding the suffix that just begins with the $sign, there are 7 suffixes. And if you listed them in lexicographic order, what's the lexicographically smallest suffix? Well, it happens to be this suffix at the end, which is just the character A, or a $sign, if you want to consider the $sign there. So 7 is the lexicographically smallest. The lexicographically smallest suffix begins at position 7. Then the next lexicographically smallest suffix begins at position 4. It's A, B, C, and so on. That's lexicographically smaller than the suffix that begins at 1, which is A, B, and then this is a D, but this is a C. C is lexicographically smaller than D, so A, B, C, and onward is lexicographically smaller than A, B, D, and onward. Okay? So the second lexicographically smallest suffix begins at position 4. And then the third lexicographically smallest suffix begins at position 1, starting with an A. And that's lexicographically smaller than suffixes that begin with B or D or C. Okay? And then the next one is at position 5. It begins with a B. And it goes BC, which is lexicographically smaller than BD. Okay, so this is a full listing of the positions of the suffixes if they were sorted into lexicographic order. Now, one of the ways that you can build a suffix array is by building a suffix tree. Here we have one. And then doing a lexicographic breadth-first search. Okay? So I'm going to go over to this board for a minute just to write this down, and then we'll come back to this in a minute. A suffix array can be built by a lexicographic depth-first search of the suffix tree for the string S, for the string that you have in hand. Okay? So I'm going to go back to this board now, and yeah, thanks. And we'll do a lexicographic depth-first search. What does it mean, the lexicographic depth-first search? It's a depth-first search of the tree, but whenever there's a choice for which edge we should take, we take the edge whose labeled, whose first character on its edge label is the smallest of the ones we haven't yet taken. Okay, so we break ties based on the string that that labels the edges that come out of the node. So initially here, we would at the root we'd go down this edge because it starts with an A, and no other edges start with A. And it's a property of a suffix tree, if you remember, that the first character labeling the edges out of any node are always different. So there's no ambiguity, no choice as to which edge we should take when we're doing a lexicographic depth-first search. So we would go on this edge, then here we would go down to, since the dollar sign is lexicographically smaller than any other character, we'd go down here. And we'd reach 7. So we mark that we've reached leaf 7. And the depth-first search comes back up to here, goes down here. Here we have a choice between going on an edge that begins D or an edge that begins C, and we take the C. Go down, we get a 4. We reach a 4. Okay? Back up, come down, we reach a 1. Back up, back up, back up. Now we're going to go down the edge that begins with a B, then with a C, we hit a 5. Back up, down to here, we hit a 2. Back up, back up. Now we take the C edge, go down to 6, and then come back up. We take this edge, we hit a 3, and hopefully this is the same string as over here. Now look at it. 7, 4, 1, 5, 2, 6, 3. So a lexicographic depth-first traversal of the suffix tree gives you a suffix array. If you just note what are the leaves that you hit, what's the order in which you're hitting the leaves as you do the depth-first traversal. And the reason is pretty immediate. The suffix tree represents all the suffixes of the string. And we're just, by doing a depth-first traversal, we're simply looking at all the suffixes. We're encountering all the suffixes. And by making it a lexicographic depth-first traversal, we're breaking any ties that we have lexicographically in favor of the smallest of the strings that extend from that node. And so we will be finding the lexicographically smallest suffix initially, and then the next lexicographically smallest, and so on. And that's what a suffix tree, that's what a suffix array is. Okay, so we know we can build suffix trees in linear time. And the traversal, the depth-first traversal, is clearly linear time too, so we know we can build a suffix array in linear time from a suffix tree. However, suffix trees in practice are actually fairly memory intensive, and they're complex to program and to build and conceptually difficult. So it was an open question for a long time whether you could build a suffix array in linear time without going through a suffix tree. Could you build a suffix array just by using a couple of arrays, let's say? You have the space for the string itself, and if you allow yourself another couple of arrays, say, or one more array even, of that basic size, could you still build a suffix array for the string? So it's not fair to build a suffix tree first. And originally, when suffix arrays were introduced by Manbear and Myers, the algorithm they gave was n log n. For a string of length n, it was n log n time to build the suffix array. And so it was an open question for a long time as to whether you can build a suffix array with that limited space in order n time. And I guess about 10 years ago, maybe less, this is 2011 right now that I'm speaking, so sometime around 2000, I don't know, 3 or 4, I think it was, three groups simultaneously came up with linear time algorithms for building a suffix array. And what I'm going to tell you about is the most elegant of those 3 methods. And this is due to Karkanen and Sanders. Okay, 2003. Yeah. Okay, so this is the most elegant of them and cute in a number of ways. So I want to generalize a little bit about a suffix array. We can talk about a suffix array for S, but restricted to the positions, well, in general restricted to some subset of positions. But in the Karkanen and Sanders method, one of these suffix arrays is going to be restricted to the positions that are 1 or 2 mod 3. Okay, so those are the positions 1, 2, but then they would skip 3 because 3 is equal to 0 mod 3, and then it would pick up with 4 and 5 and skip 6, and then it would be 7 and 8. So you're going to have a suffix array for S restricted to the positions that are 1 or 2 mod 3. Let's just writing down the suffix array over here. We have 7, 4, 1, 5, 2, 6, 3. And so restricted to positions 1 or 2 mod 3, we'd have the 7, the 4, but then we would skip the 1, we'd have the 5, the 2, skip that, and then we'd have the 3. Okay? So we would have this restricted suffix array 7, 4, 5, 2, 3. Okay. And then also in the Karkanen and Sanders method, they're going to find a suffix array for S restricted to positions that are 0 mod 3. Okay, and then so that is all the other ones. So it would be this one and this one. Okay, in this little example, and then they're going to merge these 2 restricted suffix arrays and get a suffix array for the entire string. Well, that's the game plan. Let me start telling you how do you find the restricted suffix array for positions 1 or 2 mod 3. Okay, so, well, actually, let me write out the basic game plan again, what I just said. Step 1 is, find the suffix array for the string S, but restricted to positions 1 or 2 mod 3. And then secondly, the same thing, but restricted to positions 0 mod 3. And then somehow merge the 2 restricted arrays to get the suffix array for S, for the whole string. And we're going to be able to do this in linear time. And what's really kind of amazing or cute about this this result of theirs is that many people had this basic schema and tried it, but instead of restricting the suffixes, the suffix array to positions 1 or 2 mod 3 and to 0 mod 3, they would restrict them to the even positions, or to the odd positions. Okay, so that's 0 mod 2 or 1 mod 2. Okay, so that's a very natural thing in computer science, evens and odds. We're all very used to that. So they would restrict to the even positions and the odd positions, and they could find these suffix arrays efficiently. But then the merging couldn't be done in a way that would then give you the overall order n result. In fact, the n log n time method was sort of this game plan, but well, in some ways you could view it that way, where they divided into odds and evens, but then the merging added the log n factor. Okay, but here the cute thing is that if you break it up this way, it turns out that you can merge efficiently, and we'll see that. Okay, but let's still focus on this, how we're going to find the suffix array restricted to positions 1 or 2 mod 3. And the way this begins is that you take all the positions that are equal to 1 or 2 mod 3, and you look at the 3 characters, you look at a substring of length 3 that starts at those various positions. Okay, so I'm going to actually have a longer example here, so that we can DAD, BCD, DAD, BCD, and then we're going to put 3. I think actually you can get away with just 2, but $3 signs at the end, so that any actually 2 should be enough. Any string, any substring that begins inside the real string, any substring of length 3 has either 3 characters or has one of the dollar signs. Okay, so let me write down the positions here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah. Okay, maybe I better put $3 signs because that's what I have in my written on my notes, and so in order not to confuse myself. But I think you could actually get away with this too. All right, and then I said what we're going to do is for every position that's 1 mod 3 or 2 mod 3, we're going to get a substring of length 3. So this is DAD, that's the substring that begins at position 1, and substring that begins at position 2 is ADB, and then we skip 3 because 3 is equal to 0 mod 3. So this is position 4, and that substring is BCD. 5 is CDD. It's a little tedious, but let me keep going. DAD. 8 is ADB. And stop me if I make a mistake here. Let me go to 10, BCD. 11 is CD dollar sign, and then 13 is just $3 signs. Okay, so these are the triples, the substrings of length 3, beginning at each of the positions that are 1 or 2 mod 3. And certainly you can grab these in linear time because this is just length 3, not longer than that. So linear time suffices to grab all these. And then we're going to sort these. We're going to sort these lexicographically. And how we're going to sort these lexicographically is with radix sort. So radix sort, remember, runs through on the right end of the string and picks up all the strings that are with the smallest character in there, so it would be the dollar sign, and so on. So I'm just going to assume everybody knows radix sort, and that radix sort can be implemented to run in time proportional to the total number of characters here. So radix sort can run in time proportional to 3. Well, it's actually 3 characters times 2/3 n positions, so about 2n. At any rate, order n, in order n time, radix sort can create the lists $, $, $. That's obviously the smallest one. 1, 2, I don't know what those numbers are. ADB. There's another ADB. Yeah, this should have been, what's written here are the positions where these actually begin in the string. So the triple $sign begins at position 13, and then this ABD begins at position 2, and there's another one that begins at position 8. Is that right? Go to 8. Yeah, ADB, and at position 2 is ADB. So I'm just writing down here what the strings are, what the triples are in the lexicographic ordering, smallest first, and then I'm also writing down what the original positions were. So BCD, that was at position 4. Another BCD was at position 10. Then there was a CD $sign at position 11. CDD at position 5. Position 1 had DAD, DAD, and position 7 had also DAD. Okay, so these are the triples starting at the positions 1 and 2, mod 3, in lexicographic order. And so this is the original position, but these are the sorted triples. And then we're going to have something called the rank. Well, the rank is just where these triples appear in this list, but taking account of ties as well. So this triple here is at the top of the list, so it's going to be rank 1. It's certainly rank 1 because it's the smallest. But the next one is different from it, so it's not rank 1. It's going to be rank 2. Okay. However, the next one, it's ADB. The next one is also ADB. So these are tied. So I'm going to call that also rank 2. Because at the moment, we don't know. We've only looked at 3 characters, starting at position 2 and starting at position 8. We don't know which of these 2 strings, which 2 suffixes, the one that starts at 2 and the one that starts at 8, is really the lexicographically smallest. But because right now, they're still identical. So they're both going to be rank 2. And then the next one, BCD, we have another BCD. That's rank 3. The next one is CD $sign, and that's rank 4, and it is different than the next one, so it's the only one that's rank 4. This is rank 5, and then rank 6 is again a tie. So these are the rank numbers. Okay, and in general, we can have many more ties. They don't have to be quite as simple as this example is. And again, this can be done in linear time, and we can assign these rank numbers. Then we do a kind of funny thing. We recode the string in terms of their rank numbers. Okay, so we're going to take 3 characters at a time, DAD, and its rank number, the rank number for DAD, is 6. Okay, and we're also going to well, let's just look at the ones that begin at position 1, mod 3, right now. So that would be rank 6, and the next one is C. The next one is BCD. BCD is rank 3. And then we have a DAD, which is a rank 6, and a BCD, which is a rank, BCD was rank 3, and then this one was rank 1. Okay? So those are, we're just assigning what the ranks are from here to the individual triples in the string, beginning at all the substrings, all the triples that begin at positions 1 mod 3. And then we're going to also do that for the positions 2 mod 3. So I hope this doesn't get too cluttered, but here's a triple that begins at position 2 mod 3, and that is a rank 2, and then this one is a rank 5, this one is rank 2, and then what do we got? 8, 10, sorry, A, rank 2. ADB, rank 2, and then CD dollar sign, yeah, and then CD dollar sign, that is rank 4. Okay. All right, so all I'm just saying is we look at each of these triples that begin at positions 1 or 2 mod 3, and we look at what their ranks are. Okay. Then we're going to form a funny kind of string. S prime is going to be all of the ranks that begin at positions, for triples that begin at position 1 mod 3. So it's going to be 6, 3, 6, 3, 1. So those are all the ranks of the triples that begin at position 1 mod 3. 6, 3, 6, 3, 1. And then followed by, I'll just put a little sign here to designate the middle. And then we're going to have the ones that begin at position 2 mod 3. So that's 2, 5, 2, 4. All right? And I can also write down the original positions that these triples came from. So this is the positions of the triples. So this 6 came from position, what position did it come from initially? Why do I have a 1 here? Well, it came from position 5 in here, right? This 6. Oh no, it came from position 1. That's why I have a 1 there. I was looking at that, but this is 1. Okay, so the original positions, if I've done this right, is 1, 4, 7, 10, 13, 2, 5, 8, 11. So those are the original positions of the corresponding rank numbers. Okay? All right. And then we have this string S prime, this funny string S prime, which is some reflection of S, because it came from these rank numbers, which came from S. And now, and the length of this, what's the length of this string? It's about 2/3 n. The original string was length n, and this is about 2/3 n, because we have one character, one number here for each position that's 1 mod 3 or 2 mod 3. Okay, so about 2/3 of the positions, so about 2/3 n. Okay, and now what we're going to do is recursively find the suffix array of S prime. Okay, S prime is a string. It happens to be a string of numbers, string of integers. We started with a string of letters in some alphabet. Now we have a string of integers, but it's a string, and we can think of finding the suffix array of it. Okay, and the claim is that the suffix array of S prime specifies the suffix array of S restricted to the positions 1 or 2 mod 3. So when we find the suffix array for S prime, then we will substitute all the positions for their original positions in S. Positions of the triples, and this is in S. Okay? So once we find the suffix array for S prime, then we're going to use it to find the suffix array of S, but restricted to the positions 1 or 2 mod 3. So let me just write down what is the suffix array of this. Okay, and let me just 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, a suffix array is a list of positions. So we should be talking about list of positions in here. What's the lexicographically smallest suffix of S prime? Well, I could put a $sign there if I wanted to, and then that would be the lexicographically smallest. But just looking at the real characters, it starts at position 5 of S prime. So the suffix array of S prime is equal to, it's 5, that when the position begins there. And then we have two suffixes that begin with character 2. So one here at position 6, it starts 2-5. The one at position 8 starts 2-4. 2-4 is lexicographically smaller. So the next one will be 8. And the next one after that will be 6. Okay? That's the suffixes that begin with 2. Then we have suffixes that begin with 3. One goes 3-1, one goes 3-6. Well, the 3-1 is smaller. 3-6 is the next one. Oops, that's a 2, right? 3-6. And then we have the ones that begin with 4. With a 4, that's an 11. Ones that begin with 5, there's only one of them, that's a 7. And, I did something wrong?
After 2 is 9, it's going to be 9. The length is a 9, it's not 11.
I'm not hearing you. Oh, it's 9, not 11. Yeah, I see what you're saying. Yeah. Right. 9, and then okay, I'm just going to cheat. I have a hard time doing examples in real time. Suffix array for S prime is 5, 8, 6, 4, 2, 9, 7, 3, 1. Okay, so that should be the suffix array for S prime. Okay, and how do we find it? Recursively. So at this point, we're building. I'm showing you the recursive approach or the algorithm for finding suffix arrays. We've only gotten a little piece into it or one part into it. But here I can just say we have this smaller problem of finding a restricted suffix array of length 2/3 n, and how I do it recursively. So in terms of this example, this is just magic. I mean, it exists. That's what it is. And now translate back these positions to the positions in S. Okay, so the suffix array for S in positions 1 or 2 mod 3. Well, position 5 in S prime was really position 13 in S. Okay? So that's 13. And position 2 in, position 8, where the 8 is, sorry. What did I do? Yeah. This is 5. Position 5 is really position 13 in S. Does that make sense? The 5th position in Yeah, anyway, this corresponds to this one. Okay, and 8 corresponds to 8. Isn't that lucky? And 6 corresponds to 2. Okay, and so on. Hopefully everybody sees what I'm doing. Then I have a 4, 11, 5, 7, 1. So I claim that this is the suffix array of S restricted to positions 1 or 2 mod 3. Okay, and where do we have the suffix array? Well, I guess we never wrote down the suffix array for this particular example, but let's look back over at the string. It's over here. Here's the original string. And let's look at the suffixes that begin at positions 1 or 2 mod 3. Certainly the smallest of them is at position 13. That begins the triple dollar sign. And the next one, we'll look at position 8. Where's position 8? That's here. That's ABD. That's certainly lexicographically smaller than the other string, which is ADB. No, sorry, this is ADBCD dollar sign. This is ABCDD. Okay, D being bigger lexicographically than the dollar sign, and so on. So the claim is that this is, in fact, the suffix array for S restricted to the positions 1 or 2 mod 3. So why is this right? Okay, so we have this wacky algorithm, seemingly wacky algorithm, where we take the triples, starting in positions 1 or 2 mod 3, and we sort them with radix sort, which we can do in order n time. And then we get these rank numbers, and we build this string, which is the rank numbers for all the triples that begin at position 1 mod 3, followed by the rank numbers of the positions mod 2 mod 3. And then recursively, we find the suffix array of that. Okay, and then we claim that just by translating back the positions to the original positions, we get the suffix array for the original string S restricted to positions 1 or 2 mod 3. Okay, so this is one of those things that you can convince yourself, I think, in the quiet of your own mind, that this is actually true, because of the way that these ranks were developed. Something that has a smaller rank number, its corresponding triple. This corresponds to a triple starting at 10. This corresponds to a triple starting at 7. This is lexicographically smaller than that triple. The triple starting at 10 is lexicographically smaller than the triple starting at 7 because the rank numbers are smaller. Okay? And so when you look at substrings in here that are lexicographically smaller, so let's say 363 is lexicographically smaller than 524 or whatever. It means that this corresponding substring in S, in the original string starting at position 4, is going to be lexicographically smaller than the string starting at position 5, and so on. So substrings where one substring is lexicographically smaller in S prime, its corresponding substring starting at the corresponding position in S is lexicographically smaller. With one caveat. Maybe there are some artificial substrings. Okay, let me just back up 1 minute. If I take two strings and compare them, two strings in S prime, and compare them until, let's say, on this side of the dividing line, and I compare them until they're not equal anymore, 3, 6, and 3, 1, this is smaller, and those comparisons did not cross the midline, then I'm really comparing real substrings in S. A substring that begins at position 4 and a substring that begins at position 10. and I really know that the substring beginning at position 10 is lexicographically smaller than the substring beginning at 4. That's if the comparisons in here end before we hit the midpoint. And similarly, if I take two positions over here and compare those substrings in S prime, if one becomes smaller than the other before they hit the end, then those are truly lexicographically smaller. That is truly lexicographically smaller. And the same thing over here, if I take a position on the left side and a position on the right side and start lexicographically comparing them, as long as that comparison ends before we hit the midpoint, or ends, we never cross the midpoint in those comparisons, then we're assured that the corresponding strings in S, that comparison of the corresponding strings in S was correct. And therefore, when you do a lexicographic sorting of the suffixes in here, in S prime, and you find a suffix array of S prime, it really does correctly correspond to a suffix array in S for positions 1 and 2 mod 3. This is conceptually the hardest part of this whole method, is to convince yourself that these comparisons will never, in fact, cross the midline. And the reason they don't cross the midline is to see that, just always think of the correspondence of what's really happening in the original string. If we're looking at positions here in S prime, it's effectively like comparing substrings that start in those positions, corresponding positions in S. And when you start at two positions in S, one of those two substrings, if you start comparing them, is going to be smaller than the other, or, well, it's going to be smaller than the other. You're going to eventually run into the triple dollar signs. I was about to say, or you'll run into the dollar signs. But when you do that, one of those substrings is less than the other. And this character at the end here includes dollar signs. We knew that. Because we put three, actually two would have been enough, but $3 signs at the end. So this last triple always contains dollar signs, and so does this last triple. So if you were to do comparisons and it looked like you were about to go over the midline, it won't actually happen because one of those is going to run into a dollar sign. Okay, that takes a little bit of more thought, but this is the point. The suffix array of S prime gives you the suffix array for S restricted to 1 or 2 mod 3. Okay, now it turns out that finding the suffix array for, let's go back over to here. So this is, I've told you how you're going to do at least recursively. This is recursive. You're going to find the suffix array of S restricted to positions 1 or 2 mod 3. Okay, now how do we find the suffix array for position 0 mod 3? Well, you could think that you're going to do just the same thing as we did, but if you do this recursively also, then in the analysis, the time analysis, you'll have 2 recursive calls, and then we won't get the linear time bound. So let me show you how you can do the position 0 mod 3 in order and time. All of the positions, not recursive, it's just all at once, the position 0 mod 3, given that you've done this. So the algorithm is going to do these first, and then you're going to find these, the position 0 mod 3. Of course, when you're doing this, you have some 0 mod 3 in the new smaller substrings. Okay, so here we're talking about the ones at position 0 mod 3 in S. Okay. Okay, so we have the suffix array restricted to positions 1 or 2 mod 3. Okay, and so now I'm looking at those positions 0 mod 3. And let's just write them down for the example I've been working with. So position 3, 6, 9, 12, those are D, B, C, D, D, A, A, B, C, and D double dollar sign. So these are the triples at positions 0 mod 3. And we want to know what is the suffix array of S restricted to the positions that are 0 mod 3, restricted to these positions. Okay, and we just look at the three positions there. I'm going to recast this as D5, D8, D4. It's unfortunate they're all Ds. That was a bad consequence of this example. all of the characters of position 0 mod 3. Wait a minute. This is an A. What happened? Oh, this is position 9. What is actual position 9? Position 9 is a D. Yes, D, B, C. Okay, my notes wrote it wrong. D, B, C. So they all begin with Ds, okay, which is kind of unfortunate. But what is this encoding? This is encoding the first character, and then this starts position 4, okay? And 4, if we look back at the, if we go back over here to the suffix array at positions, suffix array for S restricted to positions 1 and 2 mod 3. So we're interested in position 4, okay? Position 4, yeah, it's right here. This says that the substring that begins at position 4 is the fifth, 1, 2, 3, 4, 5, is the fifth smallest, lexicographically smallest among all the substrings that begin at positions 1 or 2 mod 3. Okay? It's the fifth smallest. And so we're encoding the substring that begins at position 3 as its first character, which is D, followed essentially by a rank number, a different kind of rank number as before, which is saying this is the substring that begins here onward is the fifth smallest of all the substrings that begin at positions 1 or 2 mod 3. And let's just do one more example. Let's take a look at position 9. Okay, starts with the D, and then the next way we've encoded this is number 4. So position 10, this is one more than 9. Position 10 is a number that's 1 or 2 mod 3, and it should be the fourth smallest. Yeah, and it is. Here we look at where where 10 is in the suffix array for S restricted to 1 or 2 mod 3, and we see that the suffix that begins at position 10 is the fourth smallest of all the suffixes that begin at positions 1 or 2 mod 3. Well, that's position 4. So we've recoded the substrings that begin at 3, 6, 9, and 12. There's the substrings that begin at position 0 mod 3. We've recoded them in 2 characters, okay? Just 2 characters. And these numbers, there are no ties for these numbers because these are position numbers in a suffix array. Okay, so no ties for those. And so now I can sort these by radix sort. Sort by radix sort in order n time. Rather trivially, these are only two columns wide. Okay, very trivially, and when I've done that, well, sort by radix sort, and I get D1, D4, D5, D8, and here are the original positions, 12, 9, 3, 6. So this is the suffix array of S restricted to positions 0 mod 3. Okay? And let me emphasize again, and we can do this in order and time. And this is non-recursive. We now have the suffix array for all of the positions 0 mod 3 in S, in the original string S, in just one order n time operation. Okay, it's not, there's no recursive call in here. And why is that? Why didn't we have to do anything recursively? Is if I had thought about finding the suffix array of S restricted to these positions in the same way that I did it for positions 1 and 2 mod 3, I would have sorted these triples and then built this funny string S prime, which represents position 0. Well, in that case, it would just be the positions at 0 mod 3. But if there had been any ties in this sorting here, which there aren't, it's D, B, C. If there had been any ties here, we would have had to recursively do the continue with the sorting, continue with the algorithm, because we didn't know, we hadn't seen beyond here, beyond the triples. But because we have these numbers, which comes from the positions 1 or 2 mod 3, we actually do have information beyond there. We do know what's beyond position 3, 4, 5. We know what's going on there and what's going on here, 9, 10, 11, 12. And those are encoded by these numbers that are here. Okay. Fine. So in order n time, we can find the suffix array of S restricted to all the positions 0 mod 3 in a non-recursive part of the algorithm. So this part is recursive, but this is non-recursive. Okay? And then once we have these two restricted suffix arrays, then we want to merge them. And this, as I said, was where the advantage of this funny way of breaking up the positions comes in. If we had broken up the positions even and odd, we'd be in trouble here in the merging in the time bound what we want. But because we broke them up in this funny way, you'll see what the punchline of this whole exercise is. Now my biggest question is, what do I do? Well, let's just do it on this board. Okay, so this was all about how we're going to find the suffix array of S restricted to position 0 mod 3, and we've done that. So now I have the suffix array of S restricted to positions mod 3, positions 1 and 2 mod 3, and the ones at 0 mod 3. And what I want is the suffix array of the original string S. So it means the suffix array for all the positions, unrestricted. So let me just write down again 13, 8, 2, 10, 4, 11, 5, 7, 1, and 12, 9, 3, 6. So this was the suffix array. This was the suffix array of S restricted to 1 and 2 mod 3. Suffix array for S at 1 and 2 mod 3. And this is the suffix array we found for S at 0 mod 3. Okay? So again, there's the string. Here's a string S, and we have these various suffixes that begin at different positions. And this is saying that we have an ordering of all the suffixes in S that begin at position 0 mod 3. So we know what the lexicographic relationship is between them. and we know what the lexicographic relationship is between these suffixes that begin at positions 1 and 2 mod 3. And here's what that is. So how do we get a suffix array for S that is an ordering of all the positions that shows the suffixes in their lexicographic order? Okay? Well, it's like merging in merge sort. So we want suffix array for S. That means all positions. So we want to merge, just completely analogous to the way merging is done in merge sort. Merge the two restricted suffix arrays. As we know that the suffix, the lexicographically smallest suffix that begins at a position 1 or 2 mod 3 begins at position 13. And we know that the lexicographically smallest suffix that begins at a position 0 mod 3 begins at 12. So the lexicographically smallest suffix overall is either the one that begins at 13 or the one that begins at 12. So we take a look at, in this case, 12 and 13. We look at what those characters are, and you just compare the characters until you see which one is lexicographically smallest. Okay? Is it the substring, is it the suffix that begins at character 12, or is it the suffix that begins at character 13? Conceptually, that's what we want to do. Conceptually, you just look at those two and compare characters until you see which one is lexicographically smallest, and then you would output that corresponding position, and then keep going exactly the same way we merge in merge sort. Okay? Let's just go over here for a moment. Position 12 and 13, at position 12, it's a D. At position 13, it's a $sign. 13 is the smaller, $sign is smaller, so 13 wins. And so back over here, we would get out, go this way, we get out 13 first, having done that comparison, and then we would compare the substring that begins at 8 versus 12, right? Let's just do that one, and I won't do much more. 8 and 12, right? So we have 8 and 12. Well, A is lexicographically smaller than D, so 8 comes out. 8 comes out in that comparison, and so on. And you can just continue to do this, and that's conceptually how you merge those two restricted suffix arrays to get a suffix array for the whole thing. So 13, 8, 2, 10, 4, 11, 5, 12, 7, 1, 9, 3, 6. Okay. All right, so that's how we want to merge, but that's not efficient. That's just conceptually what we really want to do. It's just not efficient yet. Okay, and here's where the whole beauty, I mean, in effect, the punchline of the whole thing is what I'm going to tell you next, and it's why this method, with its funny way of dividing up the positions, ended up in linear time. So, question? No. How do we do the merging? So efficient merging. Okay, so when we're merging, we're always looking at a position that's either 1 or 2 mod 3 against a position that's 0 mod 3. So let's look at these two cases. So case 1, we compare a suffix starting at position 1 mod 3, okay, with a suffix starting at 0 mod 3. Okay? So here we are. We're something that's 1 mod 3. What's a number in 1 mod 3? Like 7. And a position 0 mod 3, 27. Okay? And we want to know which of these suffixes is lexicographically smallest. Okay, we look at the first character that's there. Well, that first character is either equal or it's unequal. If it's unequal, then we know exactly which of these two substrings is lexicographically smallest. So start comparing. One character. If different, if it's unequal, if those two characters are unequal, then we can stop because we know which of those two substrings are lexicographically smallest. Okay? Just based on one character. But if they are equal, okay, but if equal, so they're equal. Now, when we want to do the comparison, we would move over to the next number, the next letter, okay? So we have some letter here, and we have some letter here. But now this position, this is a position 2 mod 3, okay? Because this was position 1 mod 3, so this is a 2 mod 3. This was a 0 mod 3, so now this is a 1 mod 3, okay? So now we're talking about comparing two suffixes, one that's at position 2 mod 3 and one that's at position 1 mod 3. And we already know how those kinds of suffixes are ordered. That information is already encoded in this restricted suffix array. So we just have to look that up. You need the right data structure that can look into here and find out which one is before the other one. But this position, which is 2 mod 3, and this position is 1 mod 3, we already know how those two suffixes compare, which is lexicographically smaller. It's in the restricted suffix array. So you just look that up. So this is just constant time to do this comparison. If one's at position 1 mod 3 and the other's at position 0 mod 3. Just constant time. So this whole business, this case is, but if this is equal, then we use the suffix array restricted to 1 or 2 mod 3. Okay? So that was that case where we're comparing positions, a suffix starting at position 1 mod 3 with a 0 mod 3. The other kind of comparison that happens in this merging is that you have something which, you have a suffix that begins at position 2 mod 3, and the other one is still a suffix that begins at 0 mod 3. Okay? So, again, you just start comparing. So 2 mod 3, what is that? Like 2 mod 3, like 2. That's the easiest, 2 mod 3. And the other one is 0 mod 3, so that's still 27, say. So again, you start out by comparing the first two characters. And if they're different, you're done. You know exactly what to do. But if they're equal, then you move over by 1. Well, now, this was a 2 mod 3, so this is, what's this position? If this was a 2 mod 3, this is now a 0 mod 3. Okay? The next position over. And the next position over here, this was a 0 mod 3, so this is a 1 mod 3. Okay? So now the problem is that the first two characters we looked at are equal, and so we want to know from the next position over which of these two substrings is lexicographically smallest. But now we have two suffixes, one that's in position 0 mod 3 and one that's in position 1 mod 3. And we just showed a minute ago that whenever you have those kind of two suffixes to look at, you can find out which is lexicographically smallest in constant number of operations. So we have this first comparison, one comparison, and then if we have to go on, we'll have a constant number of operations from there. Therefore, this case is also doable in constant time. Okay? So what we've said is that what we've shown now is that in the merging that we have to do after we find the suffix array that restricted to positions 1 and 2 mod 3 and the suffix array restricted to position 0 mod 3, when we want to merge them, the basic algorithm is like we do in merge sort, in merging and merge sort, and moreover, whenever we look at two positions, we can actually find out which of the two suffixes represented by those two positions is lexicographically smallest in constant time. And it was the point, the reason we could do this in constant time is because the suffixes begin at positions 1, 2 mod 3 and 0 mod 3, and they just have this funny property that we just discussed over here. And we'll get back in a minute to the odd-even case and why that doesn't work. But let's wrap up this method. Let's do the time analysis. Okay? Unfortunately, I erased the overall thing, but let's do the time analysis. We don't need these examples anymore. So, yeah, really don't need that. Time analysis. Well, we said step 1 was find the suffix array restricted to positions 1 or 2 mod 3. And that started out by finding triples and doing a radix sort on the triples. So that's order n for the radix sort. Then you had the ranks, and you built this funny string S prime. That's certainly, again, just order n time to build S prime. And then recursively, you had to find the suffix array, the full suffix array, of a string which had length 2/3 n. Okay? It's still up here. The S prime had size 2/3 n because it had a character for each position 1 or 2 mod 3. So recursively we do that, which itself may, that recursive call in this example finished after one more step. But if there are any ties in the ranks that get calculated, you have to keep recursing and recursing. But it satisfies this recurrence relation. So T of n is equal to order n plus T n over 2/3 n. Okay? And then we said we had to find the, but this isn't quite right, quite finished yet. We also have to find the suffix array for positions 0 mod 3. Okay? And what did that involve? Well, we showed that was non-recursive, order n time, non-recursive. Once you had done this, you could do this in order n time non-recursively. And then you had to merge and that was also order n time. And the key point was that each comparison you do in the merge could be done in constant time. So let me rewrite what this recurrence relation is. T of n is the total time to build a suffix array for a string of length n, and you have order n initially to find the triples, then recursion to find the suffix array restricted to positions 1 and 2 mod 3. Then you have the time to build the suffix array restricted position 0 mod 3, and then you have the merging, again, the merging here of those two restricted suffix arrays. And so this is just T of n is equal to order n plus T of 2/3 n. And that means it's n plus 2/3 n plus 2/3 squared n, and so on. So this means T of n is equal to n summation 2/3 to the I. Well, let's just do it. Make I equals 0 through infinity. And this is just a geometric 2/3. I think it's 3. Is that right? 1 over 1 minus 2/3. I think this sums to 3. And so we'll just call this order n. Okay? So this is the whole business, the algorithm plus the analysis that builds a suffix array in linear time, order n time. Okay. Now, let's just think for a moment about trying this algorithm where we divided the positions into even and odd instead of into these funny 3 different ways. So then we would, this would be find the suffix array restricted positions, let's say 0 mod 3, or 1 mod 3, and then find the positions suffix array of 0 mod 3. No, sorry, 1 mod 2, okay? Or 0 mod 2. Okay, so these are the odds and these are the evens, right? And then merge them, okay? So you could say the same sort of thing. You could say, all right, we're going to do this recursively. Actually, I think it's better to do this, 0 first and then 1. Okay, so you could say, well, I'm going to do this one recursively, okay, and then I'm going to do this one in non-recursive in linear time once I have this. The same kind of idea that we had before, and then I'm going to merge, okay? So you'd find the suffix array restricted to the even positions, you'd find the suffix array restricted to the odd positions, and then exactly by the logic of merging we had before, you can just merge those two lists. But now think about what you have to do when you're merging lists of like this. So in general, you're looking at two suffixes, one that begins at an odd number, let's say 5, and one that begins at an even number, 28, okay? And you want to merge these two. So again, you look at the first character. If they're different, that's great. You know that the suffix begins at position 5 here is going to be less graphically smaller than the one that begins at 28. That's fine. But if they're equal, then you move over to the next position, and the next position here, and you have to determine now which of these two suffixes that begins in position 6, say, in position 29, which of those two is lexicographically smaller? Well, the problem is this is now at an even position, this is an odd position. Okay? So you can't answer these ones by just looking into a list we already have. The wonderful thing about starting at positions 1 and 2 mod 3 versus 0 mod 3 is that we could run into queries where the two positions were in the same restricted list. The one's either 1 or 2 mod 3 or 0 mod 3. But here, that can never happen. This starts out as odd, this is even, and if we move over, this is even, this is odd. And then we move over, this is odd, and this is even again. So you're always in opposite lists. Your queries always are in opposite lists, and so there's nothing that saves you. You have to just keep going like that. And therefore, the time to merge is not linear. In fact, it looks like the time to merge would be quadratic, just for a single merging. And there was a lot of cleverness that went into the original algorithm to get n log n. But certainly you're not going to get linear time out of this, and that's why dividing into odd and even doesn't work in the way that the way this suffix array algorithm does work. But this original one was around for a long time, and I just think someday somebody woke up and taking a shower, they went, oh my God, it's just, if I did it 1 and 2 mod 3 versus 0 mod 3, everything works. Okay, so that's that. I don't have time to tell you the next piece, but I have time to introduce it, and then we'll talk about it in the next lecture. The next thing that makes suffix arrays useful, so this is how to build suffix arrays in linear time. But I didn't really tell you too much about why suffix arrays are useful. I said they're smaller, they use less space than suffix trees. But to make a suffix array most useful, well, what do I mean by that? Well, there are lots of string problems that can be solved in linear time using suffix trees. And we would like to see that all of those problems, and maybe more, can be solved with suffix arrays in linear time. Now, there's no meta theorem that says that anything you can do with a suffix tree in linear time, you can do with a suffix array in linear time. But over time, people have seen how to solve various string problems that are done in suffix trees in linear time, how to do those problems in suffix arrays in linear time. And an almost essential component of those algorithms is something called the LCP array. Okay, to make a suffix tree most useful, we need or want the LCP array for S. And one of the things, for example, that you can do with the LCP array and the suffix array for S is you can build a suffix tree in linear time. I haven't even told you what LCP array is, but let me advertise something for it. For example, with the suffix array for S and the array LCP for S, one can build a suffix tree for S in order n time. You build it with the suffix array and you build it with this LCP array. Of course, you could always do this. This is a vacuously true statement if I just ignore the suffix array and the LCP and then use the algorithm to build a suffix tree in linear time. But I don't mean that. That would be silly. I mean, with the suffix array and with the LCP array, there's a fairly simple algorithm that can then construct a suffix tree. And so, in fact, today, 2011, when people want to build a suffix tree, typically now, instead of using the beautiful classical algorithms like Yukonen's algorithm for building a suffix tree, they will build the suffix tree with this approach. First build a suffix array in linear time, then build this LCP in linear time, and then use those to construct the suffix tree in linear time. Okay, let me tell you what LCP is, and then next time I'll show you how to compute the LCP array in linear time, which was also an open question for a long time. It's funny, the question of building a suffix array in linear time was open for a long time, and then three groups discovered it all at once. And you might want to say, well, that's because something must have come out 6 months earlier that showed everybody the way. But it's not true. There's nothing that seemed to have provoked those three different groups. It's just pure coincidence. The question had been open for a long time, and there was no new advance 6 months prior or something like that. And the same thing for LCP. It was an open question for a long time, and then it was finally answered, and with ideas and that could have been done years before. But all right. So what is LCP? So we still have a suffix array. Well, let me do it first abstractly, and then I'll show that. Well, maybe I'll end after I define this abstractly. So here we have a suffix array. And now, okay, I'll just give you one. 13, 8 to 10, 8 to 10, 4, 11, 5, 12, 4, 11, 5, 12, 7, 1, 9, 1, 9, and then I think it ends 3, 6. Okay. So there's a suffix array. It happens to be the suffix array for this string. No, it isn't. It's the suffix array. Yes, it is. It's for this string, right? Yeah, okay. So this is the suffix array for this string. Okay. And I wanted to find predecessor of k, and that is the position. This is the definition. Position of the entry in the suffix array just before the entry for k. All right, so this is a little bit tricky. So, for example, the predecessor of 4. So this is what k is. K is equal to 4. Where is 4 in the suffix array? It's in position 1, 2, 3, 4, 5. Okay? And the position just preceding that is this one, and the value that's there is 10. Okay? Let me do another one. Let's say predecessor of 12. Okay, we find out where 12 is, and that's at position 1, 2, 3, 4, 5, 6, 7, 8. And just prior to that has a value or entry of 5. Okay? Now, why are these of interest? Why are we interested in k related to the predecessor of k? Because in the suffix array, two positions, these are positions of suffixes in the string s. If they're neighbors, if they're adjacent, that means that the two suffixes are pretty similar, at least initially. Okay, this is the suffix that begins at position 5 is lexicographically smaller than the suffix that begins at 12, but it's the one that's most similar, lexicographically similar to the suffix that begins at 12. So neighboring entries in the suffix array represent suffixes that are relatively similar, at least at their beginning, and then they deviate at some point. Okay, so this is not just totally crazy. And so what the LCP array is, LCP stands for longest common prefix, or the length of the longest common prefix. So LCP of k is equal to the length of the longest common prefix, or length of the common prefix, the longest common prefix between the suffix in S starting at position K and the suffix starting at position pred K. So again, an example, if K is equal to 12, okay, pred 12 is equal to 10, no, is equal to 5, sorry. And so what this is asking for is, what is the length of the longest prefix starting at position 5 and starting at position 12? Because these are two neighboring values in the suffix array, we know that these two suffixes are fairly equal. Well, they may be quite similar at the beginnings. So in fact, if you go back over to the string here and you look at position 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, well, okay, they're not very, they happen to be neighbors in the suffix array, but they're not terribly similar. They differ in the first character. And so in that case, the LCP of 5 and 12 is equal to 0. Okay, but that's what this sorry, the LCP of 5 is equal to 0. And did I say that? No, LCP of 12. Is equal to 0. And with these values, LCP, along with the suffix array, you can do solve many string problems in linear time. And perhaps I'll show you one during next lecture, but the main thing in next lecture is to describe how to construct the LCP values in linear time, order n time. Okay, well, I've run out of time for this lecture, and we'll finish this whole business next time. Thank you.